would like to welcome to the stage to Arnaud Gazda. He's a quantum development lead at EVIDEN, and he's going to talk about from NISQ to hybrid computing.
Good morning, everyone. So can you hear well? Okay, great. So it's really a pleasure to be here to meet you all. So today I'm going to present from NISQ to hybrid computing, and it's to share our vision on how the programming of quantum processing units will evolve to be more compatible with HPC. So my name is Arnaud Gazda, and I am the tech lead of the EVIDEN Quantum Lab, and I am based in the Paris area. So first, we will start with a very quick definition of quantum computing. So quantum computing means using quantum mechanics to solve computational problems. So it promises exponential speed up to solve specific problems, not all of them, unfortunately. And it will be used in HPC because high-performance computing is the field where we try to reach the limits of computing. And there is a long path, a long way to travel to go from where we are today, which is called the NISQ era, to the use of quantum computing in HPC application. So when I'm talking about quantum computing in HPC application, it doesn't really mean having a quantum computer in a HPC cluster, but using quantum processing units inside a useful application. So in fact, obviously, we need to improve the quantum hardware, but we also need to understand what a hybrid quantum classical application is and how it should evolve to, and it will have obviously an impact on how we program on QPUs. So in fact, today we are in the NISQ era, so we'll use a classical computer to describe a quantum computation, and we'll send this quantum computation to a quantum processing unit, and you will get back the results. In fact, there is no persistency of the information on the QPU. We send the information, and when the result is sent back, all the information is removed from the QPU. There is no persistency of the quantum memory, and so on. But when we're talking about hybrid computing, we really want to use both classical resources and the accelerator. And we will perform two computations in parallel, and we'll have a lot of communication during the computation. And what we want to do is to be able to switch from the NISQ era, in blue, to the hybrid computing era for quantum computing. So in fact, this presentation is mainly focused on digital computing. So yesterday, thanks to the Kilimanjaro presentation, you learned that there is multiple paradigms in quantum computing. This presentation is more about the gate-based programming and not the analog programming. So this presentation is split in 4 parts. First, we will give a proper definition of what the NISQ era is and what the HPC, high-performance hybrid HPC is. Then we will see how hybrid computing may be adapted to quantum computing, and we'll give you then an example of such framework to perform hybrid programming for quantum processing units. So first, a quick definition of the NISQ era. So NISQ means noisy intermediate scale quantum. It's an adjective which is used to qualify the current state of the art of quantum computing. So when we're talking about NISQ, we are talking about QPUs or algorithms composed of 10 to hundreds of qubits. We will have access to noisy qubits. So when we will perform a computation on these qubits, it won't perform the exact computation we want to do. And so it's today's state of the art. So when we are talking about NISQ, we are talking about short-term vision. So the purpose of the NISQ era is to demonstrate that there is a quantum advantage. So it's to prove that we can use quantum computing to do useful things. So obviously, we will focus on the pure quantum part. We want to simplify as much as possible the way we program these QPUs. So we'll likely use prototyping languages like Python because we don't want to add a complexity. Because the QPUs are noisy, we will try to perform a very short computation. We don't want to have a computation that lasts in the time, because due to the noise phenomena, it will destroy the computation. And also, there is a low availability rate of the hardware, because in fact, the QPU are noisy, and to mitigate the noise, we'll have to do a lot of calibration, and we have to remove the QPU from the HPC cluster. So in fact, it's a device that is not always available for the users. When we are in a high-performance quantum computing era, we'll have access to thousands of perfect qubits. So when we're talking about perfect qubit, it doesn't mean that the qubit on the QPU itself is perfect, but we'll have some layers that will provide logical qubits which are perfect for the user point of view. The idea is when there is a quantum advantage, we'll want to use quantum computing in a practical application. So we'll design HPC applications that we will use both classical and quantum resources. And since the QPU are ideal, we'll be able to perform a long computation, a computation that lasts in the time. So maybe a computation that can perform during several hours, which is totally not possible today. And as any HPC device, we want the QPU to be fully available and easily accessible. And we are in the NISQ era. So today, when we are talking about quantum computing, we'll likely use the circuit formalism. So it's a very simple structure. So you can see it as a timeline. And each line corresponds to 1 qubit, so quantum memory. And we'll dispatch the instruction on this timeline. So we first start with a basic gate here, and we dispatch the quantum instruction on this timeline. It's very easy to understand. It's very user-friendly. It's fast to execute because all the information, all the instructions are encoded in this structure. So the QPU doesn't have to wait for the next instruction. So it's very fast for the QPU to execute the quantum circuit. And it's also a technique to reduce the noise on the QPU. But in fact, it does not really scale, and it's really static. So you cannot really insert classical instructions, so classical processing, in this structure. So it's not really convenient to perform hybrid computing. There are some proposals which does not correspond to hybrid computing, is to have a classical process that will create multiple independent quantum circuits and set them one after the other, and depending on the results, the CPU will create a new quantum job. But in fact, this way of describing a quantum program will change because of the quantum error correction. So the error quantum correction follows this very simple process. So in fact, we will measure what we call a syndrome on the QPU. The result of the syndrome will be sent to the CPU, and the CPU will try to analyze, based on what has been measured on the QPU, what error occurred on the QPU. And it will try to design a sequence of instructions to fix this error. And so in fact, we will pause the quantum computation, but we keep the quantum memory on the QPU. And the CPU will be used to decide which instruction will be executed next. And then it has an impact on the QPU, and we loop until no error is detected. So in fact, to do that, we will use something like that. So we'll plug a QPU to the host, and the QPU will be composed of two things: the controller, which is a classical object that will receive the instruction from the host and try to schedule quantum instruction on the quantum part. The controller will be responsible of a lot of things, including the quantum error correction. So it doesn't really mean, so maybe we can send a circuit to the controller, and it can perform the quantum error correction, but maybe we can also have another kind of paradigm. Yeah. So in fact, when we have a very big picture, we can see that the way the QPU will look like will be way more similar to what we have in classical computing, in hybrid classical computing, like CPU, GPU. So, yeah. So, in fact, the classical programming framework, hybrid framework like CUDA and so on, allow really hybrid computing when we can have a fine communication between the host and the device, and the host can send instruction to the device dynamically. We are not using static computation when we are performing hybrid computing with GPUs. And in fact, we don't really want to have the same, so we want to have the same thing for QPUs as GPU. We don't really want to have static communication with the QPU, and we can already witness some quantum algorithms that need this dynamic interaction between the classical part and the quantum part. Here is a very simple example, so I won't really go into the detail of this program, but here we have some quantum instruction, and we will measure something, and we will process classically what we have extracted from the QPU. And the result of this classical computation will be used to decide which instruction should be executed next on the QPU. So in fact, we are in a scheme which is really similar to what we have for quantum error correction, and we really want to change the way we communicate with the QPU and how we develop algorithms to do that. So, in fact, when we do hybrid classical computing, so we will likely use a GPU. So, we already have some ideas of what hybrid computing looks like, because we are currently doing that in classical computing. So, in fact, we will connect the GPU to the host using a connection like a PCI Express connection, and we will use high-performance programming languages to target the GPU, like C, C++, Fortran. And in fact, we will use some programming frameworks to create some application to target the GPU. So there are other frameworks that still exist, but we can split the framework in two kinds of categories, like OpenCL or CUDA, which introduce a new programming language. But there is also some language extension, like OpenMP or OpenACC, that provide some pragmas in the programming language to extend the behavior of the classical programming language. So I will focus on the language extension, so OpenMP. So if you want to target a GPU using OpenMP, you will do something like that. So you will create a C++ application that will run on the CPU, and you can use a Pragma OMP target to say that the following scope will be executed on the GPU. And we want to have the same thing for the QPU. So we designed a framework which is called Q-Pragma, and it's really similar to what we have. So we will write down a C++ application that will run on the CPU, but we can create some scope and decorate them using a Pragma quantum scope Pragma to say that the following statements should be executed on the QPU itself. So in fact, there is no for loop because QPUs are not really designed for parallel processing, but it's really similar between the CPU and the GPU and CPU and QPU. Sorry. So in fact, Q-Pragma also allowed to have this kind of very thin interaction between the CPU and the QPU, because we can do, and it's really useful to do very advanced programming and create some quantum states that are not trivially created using a basic circuit. So here is a very basic example. So first we will create two quantum registers. The very first one will be a register of 8 qubits, which will be interpreted as a quantum integer. And the second register will be the ancilla, which is a quantum bool, so very similar to C++, so it's a qubit. We will reset the very first register. So reset is not really reversible, but we can measure a register and apply a is gate where we measure a 1. So it destroys the state, but it's a function that will ensure that the register will be to state 0. So yeah. We will apply a wall of Hadamard gate to create a uniform superposition between 0 and 2 to the power of 8 minus 1. And we will use the Pragma quantum control. So the Pragma quantum control can be seen as a if in classical computing, but it's a quantumized version of the if. So we will, so in fact, we will apply X gate, or the X gate will have an impact only if the condition passed to the Pragma control is considered to true. So in fact, it will create the following state. So it will apply the X gate only if quantum int is greater than 200. So we will get the following state. And we'll measure the second qubit. And if we measure 1, it means we projected the quantum state in the wrong space. So we restart. And we have a very dynamic interaction between the CPU and the QPU, a classical part and the quantum part. So we introduce a new programming framework called Q-Pragma that introduces a set of pragma to extend the behavior of C++. So we have two pragmas called Pragma Quantum Scope and Pragma Quantum Move to select the code locality. So it's a kernel and memory management. It's used to decide if a sample of code is executed on the CPU or on the GPU, and also to decide if some memory should be stored on the CPU or on the GPU part. And we have also some pragmas to add some quantum capabilities to C++. So the Pragma Quantum Routine, Pragma Quantum Control, and Pragma Quantum Compute. I will give you some example of this pragma a little bit later. So in fact, these pragma are not really coming from nowhere. So we try to define a proper definition of what a hybrid programming framework should look like. So a hybrid programming framework should be able to manage the code and memory locality. So where a code is executed, where a variable is stored, if it's on the CPU or on the GPU. We need to be able to do dynamic interaction, so a lot of communication between the host and the device. We also need to have a scalable framework, which is able to create, so we should be able to use this framework to create very large application, because we're in HPC. So these are quite known in classical computing, and there is also the typing, which is really important, because we want to have a framework that can scale, but it should also scale from the user point of view. So the typing, so being able to introduce type in the framework, is also a way to create a layer of abstraction that can simplify the way applications are designed. And we also need to add quantum capabilities to this framework. So every quantum instruction can be reversed. So we need to be able to exploit this property in the quantum programming framework. If any quantum instruction is controllable. So we need also to be able to exploit this property in the quantum programming framework. And the last one is the safe end computation, which is a very specific word. Maybe you haven't really heard of it. It's a mechanism used to reset a register. So in fact, if you have two registers in quantum computing, these two registers may be entangled. So if you take a register, you allocate a register, and you want to ensure this register is set to 0, you will likely perform a non-reversible operation on it. And because these two registers are entangled, it may have a side effect on register you don't really want to touch when you allocate this register. So in fact, there is a safe uncomputation mechanism is when we allocate a register, we will perform some computation to change state. We'll have to apply exactly the operation we did, but in the reverse version, to ensure that this register is reset to 0 when we release it. Like that, we ensure that if this register is reallocated later, there is no bad consequence of using it. So in fact, we try to do a summary of what is supported by existing framework, and we saw that there is no framework today that match all these features. So there is no framework for HPC for hybrid computing. So in fact, we decided to design Q-Pragma, which is a C++ framework that introduces some quantum types to allocate quantum memory, but also introduce some pragmas to extend C++ to be able to do hybrid classical quantum computing. So I will give you some examples. So you can create a quantum kernel using the Pragma quantum routine. So you will use the same syntax as a C++ function. So here you will create a kernel, and a kernel is callable as any C++ function. You can have an inverse version of this kernel, because a kernel is reversible, and you can also control this kernel. And here are some examples on how we use this kernel, so we can call it as any C++ function, apply call an inverse version, which is a .dag, and apply a control version of this kernel. There is the Pragma quantum control, so it's the example I showed you earlier, but we can use Pragma quantum control to change the scope and apply a control version of the scope. And there is the Pragma quantum compute, which is used to simplify the management of the safe uncomputation. So when we'll initialize a register, we'll put it in a Pragma quantum compute, and we'll have the guarantee that all these instructions will be reversed when we'll freeze this register. Yeah. And to conclude, I will give you a more advanced example. So here is how you would route the Shor algorithm using Q-Pragma. So the Shor algorithm, so it's only the quantum part. I missed the classical part, but the Shor algorithm is used if you want, for instance, to break a RSA crypto system. So it can be wrote down quite easily using Q-Pragma. So the paper has been published. So if you want to scan this QR code, you can read all the paper. And thank you very much for your attention.
Pragma implementation looks beautiful, so it's
thank you.
Really, really good. Do we have any questions from the audience? Yes.
It's a simple question, and I think I know the answer, but I need to ask. It's only for the evidence quantum architecture. It's not a global feature for any quantum infrastructure or something like that.
Yeah, so for now it's only a toy for the EVIDEN labs. We want to open it. We are still getting some feedbacks to improve the framework and maybe make it more robust. At some point we want to make it open source, so to be open to the community. Yeah, so it's introduced a lot of features. Because it's really also user-friendly, you will likely allocate a lot of qubits. And if you use a Q-Pragma, if you create a Q-Pragma program, you will likely not be able to find any QPU capable of running your application.
Yeah,
so, yeah.
Say, for example, it's not possible to use Minimise Yaro supercomputer or in another one. It's only for a specific one. And need some adaptation in the compiler for the other ones. No? This is the
I guess that this is the result of a very new and cutting-edge technology. So there's a lack of standards. There's a lack of so it's good to see that one of the first steps is getting this into OpenMP, which is pretty simple to use. Awesome. Thank you so much.
Thank you.